Quantum physics did not begin as an attempt to make science more mysterious. Quite the opposite. It began as an attempt to clean up a mess. Hello, and welcome to Sleepy Space Traveler. Today, we're going to explore quantum physics, not as a collection of intimidating equations or abstract ideas, but as a story about how the universe actually works at its deepest level. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. And wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm, I hope this time feels peaceful. I hope your mind can soften and this moment can become a pause in your day. Thank you for being here. Now, let's begin. By the late 1800s, physicists felt confident they were close to finishing their understanding of the universe. Newton's laws described motion. Maxwell's equations explained electricity, magnetism, and light. Thermodynamics governed heat and energy. The universe appeared orderly, predictable, and deeply mechanical. There were, of course, small gaps, a few unexplained details, but many scientists believed these would be patched up with minor adjustments. One famous physicist even suggested that future students should avoid physics entirely because everything important had already been discovered. That confidence did not survive long. The trouble began when scientists looked too closely at things that were too small, too hot, or too bright. One of the first cracks appeared in the study of heat and light. Physicists wanted to understand how objects glow when heated. A hot piece of metal, for example, emits light. As it gets hotter, the color changes from red to white to blue. This seemed straightforward until someone tried to calculate it. Using classical physics, scientists predicted how much energy an object should emit at different wavelengths. The equations worked reasonably well at long wavelengths, but at short wavelengths, something absurd happened. The equations predicted infinite energy, not just a lot of energy, literally infinite. According to classical theory, a hot object should release unlimited ultraviolet radiation. This contradiction became known as the ultraviolet catastrophe. Clearly, something was wrong. The universe does not produce infinite energy every time you heat an object. The problem was not experimental error. The problem was the theory itself. This is where Max Planck entered the story. Planck did not set out to overthrow physics. He was deeply conservative in his thinking. He wanted to fix the equations, not rewrite reality. But to make the math work, he introduced an idea that would quietly explode everything. He proposed that energy could only be emitted or absorbed in discrete amounts, small packets, rather than flowing smoothly. These packets were later called quanta. To understand why this was radical, imagine how we normally think about energy. If you turn a dimmer switch, the light smoothly brightens. You expect energy to change continuously, like water flowing from a tap. Planck suggested something different. Energy behaves more like a staircase than a ramp. You can stand on one step or another, but not halfway between them. At first, Planck thought this was just a mathematical trick, a convenient fix. He did not believe it described reality, but reality disagreed. Soon after, Albert Einstein applied the same idea to light itself. Classical physics treated light purely as a wave, like ripples on water. But experiments showed that light could knock electrons out of metal surfaces only if the light had enough frequency, regardless of intensity. More brightness didn't help. Only higher frequency did. Einstein explained this by proposing that light comes in packets too. We now call them photons. Light, it turned out, behaved like a particle. This was deeply uncomfortable. Waves spread out. Particles are localized. Classical physics insisted you had to choose one. Quantum physics refused. Then things got worse. Physicists discovered that not only light, but matter itself behaved strangely. Electrons, tiny particles we thought of as point-like objects, sometimes acted like waves. They interfered with themselves. They produced patterns no particle should produce. The famous double-slit experiment made this impossible to ignore. Fire electrons one at a time through two narrow slits, and over time, they build an interference pattern, exactly what waves do. But detect which slit an electron goes through, and the wave pattern disappears. The electrons behave like particles again. This was not a technical glitch. It was repeatable, reliable, inescapable. The universe was telling physicists something very clear. Our classical categories were wrong. Light is not just a wave or a particle. Matter is not just matter. Reality does not conform to everyday intuition when you shrink it down far enough. Quantum physics emerged as a response to this fact. It was not optional. It was not philosophical. It was required for the equations to match experiments. One of the hardest adjustments was abandoning the idea of certainty. Classical physics assumes that if you know enough information, you can predict the future exactly. A thrown ball follows a precise trajectory. A planet follows a precise orbit. Quantum physics does not work that way. At the quantum level, the best you can do is calculate probabilities. You can say where an electron is likely to be found, not where it definitely is. You can predict the odds of decay, not the exact moment it will happen. This was not due to poor measurement tools. It was not ignorance waiting to be corrected. It was fundamental. Werner Heisenberg formalized this realization with the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be known exactly at the same time. This is often misunderstood. The uncertainty principle does not mean we are clumsy observers. It means nature itself does not assign precise values simultaneously. The limitation is not technological, it is structural. An analogy helps. Imagine trying to photograph a hummingbird's wings. If you freeze the motion perfectly, you lose information about speed. If you capture speed accurately, the position blurs. The limitation comes from how the system behaves, not from your camera. Quantum systems behave in a similar way, but more fundamentally. As physicists continued developing the theory, they realized that particles are described not by exact trajectories, but by mathematical objects called wave functions. These wave functions encode probabilities. They evolve smoothly over time according to Schrödinger's equation. But when you measure the system, the wave function appears to collapse into a specific outcome. This raised a disturbing question. What counts as a measurement? Is it a human observer, a detector, an interaction with the environment? Quantum physics itself does not clearly say. This ambiguity led to decades of debate and multiple interpretations. Some physicists argued that measurement plays a special role. Others proposed that all possible outcomes happen, branching into many worlds. Others focused on decoherence, where interaction with the environment makes quantum behavior effectively classical. Importantly, all these interpretations agree on the predictions. They differ on what the math means. That is unusual in physics. Usually, disagreement means someone is wrong. In quantum physics, disagreement often means the theory works, but our language struggles to keep up. Despite this strangeness, quantum physics is astonishingly successful. It explains atomic structure. It explains chemical bonding. It explains why stars shine, why matter is stable, why electronics work, why lasers exist, why your phone functions. This is not speculative science. It is tested to extraordinary precision. The reason quantum physics feels unsettling is not because it is vague or mystical. It is unsettling because it forces us to accept that reality does not behave the way we expect. The universe is not built from tiny billiard balls bouncing around in empty space. It is built from systems that exist as possibilities until interactions force outcomes. In the next part, we will dig deeper into this idea of quantization and wave-particle duality, using clear analogies and concrete experiments to show how reality shifts when we zoom in. By the time physicists accepted that energy comes in discrete packets, they were already standing on unfamiliar ground. But quantization alone was only the beginning. The deeper shock came when scientists realized that the universe does not respect our intuitive categories. In everyday life, things fall neatly into boxes. A car is not a wave. A sound is not a particle. Water can splash, air can flow, and rocks can be kicked. We expect objects to behave consistently based on what they are. Quantum physics breaks this expectation immediately. At small scales, nature refuses to commit. To understand why this is such a problem, we need to talk about waves and particles, not as abstract ideas, but as behaviors. A particle, in classical terms, is something localized. You can point to where it is. You can track its path. Throw a ball, and it follows a trajectory. If you miss it, it lands somewhere specific. A wave, by contrast, is spread out. It doesn't have a single location. Ocean waves pass through a buoy without carrying the buoy forward. Sound waves move through air, while air molecules mostly stay put. Waves interfere with each other, creating patterns of reinforcement and cancellation. For centuries, physics treated waves and particles as mutually exclusive categories. Then light ruined everything. Light had always behaved like a wave. It diffracts, interferes, bends around obstacles. These are textbook wave behaviors. But when Einstein explained the photoelectric effect, light suddenly behaved like a particle, delivering energy in precise parts. Physicists tried to live with this contradiction by saying, light is sometimes a wave, sometimes a particle. This didn't last, because electrons joined the rebellion. Electrons had always been considered particles. They have mass. They carry charge. They orbit atomic nuclei. But when scientists fired electrons through the double-slit experiment, the results were unmistakable. The interference pattern appeared, not because electrons were colliding or bouncing, but because each electron behaved as if it went through both slits at once. This wasn't metaphorical language. The math required it. The pattern could not form unless each electron's behavior was wave-like. Here's where intuition completely collapses. If you fire water droplets through two slits, you get two piles. If you fire bullets, you get two piles. If you fire waves, you get interference. Electrons, fired one at a time, produce interference. This means the electron cannot be thought of as a tiny marble following a single path. But it also cannot be thought of as a wave made of something spread out like water. It behaves like neither. The modern way to say this is that electrons, and all quantum objects, are described by wave functions. These are not physical waves in space like sound or water. They are mathematical objects that encode probabilities. The wave function tells you where the electron might be found if you measure it. Before measurement, the electron does not have a single definite position. It exists as a set of possibilities. This idea often triggers resistance, so an analogy helps. Imagine a weather forecast map showing the chance of rain across a region. The map is not claiming that rain is falling everywhere at once. It is describing probabilities. When rain actually falls at a specific location, that outcome becomes real. Quantum systems behave similarly, but with one crucial difference. In weather, probabilities reflect ignorance. In quantum physics, probabilities reflect the structure of reality itself. This distinction is essential. If you don't know where your keys are, that's ignorance. The keys still exist in one place. In quantum physics, before measurement, the system does not possess a single definite value in the same way. This is not philosophical speculation. It is the only framework that matches experimental results. The idea that a particle exists in multiple possible states at once is called superposition. Again, this term sounds mystical, but it's not. It simply means that the wave function contains multiple allowed outcomes simultaneously. Superposition does not mean everything happens at once in a chaotic way. It means the system evolves according to precise rules that preserve all possible outcomes until an interaction forces a result. Here's a grounded analogy. Imagine you're flipping a coin, but instead of landing immediately, the coin keeps spinning in the air indefinitely. While it spins, it's not heads or tails. It contains the possibility of both. Only when it lands does the outcome become definite. Quantum systems are like coins that stay spinning until they interact. Measurement is the landing. But what counts as a measurement? This question bothered physicists deeply. Is measurement something special that humans do? Or is it just any interaction that transfers information? Most modern physicists favor the second view. Measurement is not magical. It's about interaction. When a quantum system interacts strongly with its environment, its delicate superposition becomes effectively locked into a specific outcome. This process is called decoherence. Decoherence explains why quantum effects disappear in large objects. A baseball interacts constantly with air molecules, light, thermal vibrations, and surrounding matter. any superposition would be destroyed almost instantly. That's why you don't see people in quantum superpositions walking through walls. Quantum behavior dominates where systems are isolated, cold, small, and carefully controlled. Another deeply unsettling feature of quantum physics is discreteness. In classical physics, quantities change smoothly. Speed increases gradually. Energy rises continuously. Quantum physics says otherwise. Electrons in atoms can only occupy specific energy levels. They cannot exist in between. When an electron jumps from one level to another, it does not travel through intermediate states. It transitions abruptly. This is why atoms emit light at precise frequencies. Each jump corresponds to a specific energy difference. Think of a staircase again. You can stand on step 1 or step 2, but not halfway between them. No matter how small your feet are, the structure does not allow it. This quantization explains the stability of matter. Without it, electrons would spiral into nuclei and atoms would collapse. Quantum physics didn't make the universe weird. It revealed the rules that keep the universe from falling apart. But quantization and superposition together introduce something even stranger. Context matters. The outcome of a quantum experiment can depend on how you choose to measure it. This is not observer bias. It is not psychology. It is built into the structure of the theory. Measure an electron's position precisely, and its momentum becomes uncertain. Measure its momentum precisely, and its position spreads out. This is not a limitation of instruments. It is a trade-off enforced by the mathematics. The universe, at its core, refuses to give you all information at once. This forces a shift in how we think about reality. Instead of asking, "What is this object doing right now?" quantum physics asks, "What outcomes are allowed and with what probabilities?" Reality becomes less like a script and more like a menu. You don't get everything. You get one selection per interaction. Despite how strange this sounds, the predictions are extraordinarily accurate. Quantum electrodynamics, the quantum theory of light and matter, matches experiments to more than 10 decimal places. If quantum physics were merely philosophical, it would have failed quickly. It didn't. It works. And because it works, we are forced to accept that the universe is not built on either or logic. It runs on both and until interaction forces a choice. In the next part, we'll move from wave functions and superpositions to uncertainty, probability, and why randomness in quantum physics is not the same as chaos or ignorance. If superposition challenges our sense of what things are, then uncertainty challenges our sense of what things do. This is where many people first hear about quantum physics in a distorted way, often summarized as, "Nothing can be known for sure." That phrasing is catchy, but it's wrong in an important way. Quantum physics is not saying that nature is sloppy or vague. It's saying that nature is precise in a different language than we are used to. The most famous statement of this idea is the Heisenberg uncertainty principle. It's often described as a limit on measurement, as if better tools might eventually get around it. But that interpretation misses the point. Uncertainty in quantum physics is not about human clumsiness. It's about how the universe itself is structured. To see why, let's start with something familiar. Imagine you're driving a car. You can know exactly where the car is parked, and you can also know exactly how fast it's moving down the highway. These two pieces of information don't interfere with each other. In classical physics, position and speed are independent properties. Knowing one doesn't blur the other. In quantum physics, this independence disappears. For particles like electrons, the more precisely you define position, the less precisely momentum can be defined, and vice versa. Momentum here isn't just speed, but speed combined with direction. This trade-off is not negotiable. It doesn't depend on how careful you are. It doesn't depend on technology. It's built into the mathematics that accurately predicts experiments. A useful analogy is sound versus time. If you hear a short, sharp sound like a clap, you know exactly when it happened, but you don't know its precise pitch. If you hear a long, steady note, you know its pitch precisely, but you can't pinpoint when it started or ended. This isn't because your ears are bad. It's because time and frequency are mathematically linked. Narrowing one spreads the other. Quantum uncertainty works the same way. Position and momentum are linked through wave behavior. A sharply localized wave requires many wavelengths combined together. A single, clean wavelength spreads out over space. This means uncertainty is not a bug. It's a feature of wave-like systems. What makes quantum physics uncomfortable is that particles are wave-like in exactly this sense. Now comes the deeper shock. Quantum uncertainty is not hiding certainty underneath. In classical systems, randomness usually reflects ignorance. If you roll dice, the outcome is determined by forces you don't track. In principle, a perfect calculation could predict the result. Quantum randomness is different. When an excited atom emits a photon, the exact moment of emission cannot be predicted. Not because we lack information, but because the theory does not contain a hidden timer. Experiments have tested this again and again. No deeper variable has been found that restores determinism. This disturbed Einstein deeply. He famously said, "God does not play dice." But every experiment since has answered back. The dice are real. However, quantum randomness is not chaos. This distinction matters. Chaotic systems are unpredictable because they are extremely sensitive to initial conditions. Weather is chaotic. Small errors grow large over time, but weather is still deterministic underneath. Quantum randomness, by contrast, is statistical but stable. While individual outcomes are unpredictable, large numbers of events follow exact probability distributions. Radioactive decay is a perfect example. You cannot predict when a specific atom will decay, but you can predict with extraordinary accuracy how many atoms in a sample will decay over a given time. This reliability is so strong that it's used in nuclear clocks and dating methods. So, quantum physics replaces certainty about individual events with certainty about patterns. It's like knowing that a casino will make money even though you can't predict the next spin of the roulette wheel. This probabilistic structure is not a philosophical compromise. It is the most accurate description we have of nature at small scales. One of the strangest consequences of this structure is that measurement outcomes are not revealed. They are created. That sentence often triggers discomfort, so let's unpack it carefully. In classical thinking, measurement uncovers a pre-existing property. You measure the temperature of water, and the water already had that temperature. In quantum physics, some properties do not exist in a definite form until measured. For example, an electron does not have a definite position prior to measurement in the same way a marble does. It has a probability distribution. When you measure it, you don't discover where it was hiding. You force the system into a specific outcome. This doesn't mean consciousness causes reality. It means interaction matters. Any interaction that extracts information, collision, absorption, emission, counts as a measurement. The universe is constantly measuring itself. Another concept that emerges here is quantum indeterminacy versus ignorance. If you shuffle a deck of cards face down, you don't know which card is on top, but the card is already determined. That's ignorance. In quantum physics, before measurement, the system genuinely does not have a single outcome stored somewhere waiting to be revealed. This has been tested using Bell's inequalities, experiments designed to detect hidden variables. The results consistently show that no local hidden variables can reproduce quantum predictions. Nature is not secretly classical underneath. It really does operate probabilistically. This leads naturally to questions about reality itself. If outcomes are probabilistic, what does that say about causality? The answer is subtle. Quantum physics preserves causality in an averaged sense. Information cannot be sent faster than light. Effects still follow causes statistically, but individual events are not rigidly determined. This is not freedom in the human sense. It's structural openness. The universe allows multiple futures, weighted by probability, until interaction selects one. This framework turns out to be essential for chemistry, biology, and technology. Without quantum uncertainty, electrons would collapse into atomic nuclei. Without probabilistic transitions, chemical bonds would not form correctly. Life itself depends on quantum rules operating quietly in the background. Even processes like photosynthesis exploit quantum coherence to efficiently transfer energy. Quantum randomness is not noise. It's a stabilizing feature. In the next part, we'll explore one of the most counterintuitive consequences of all this: entanglement. The phenomenon that led Einstein to talk about spooky action at a distance, and which forces us to rethink separation, independence, and locality itself. If uncertainty unsettles us by removing certainty from individual events, entanglement unsettles us by removing independence itself. This is where quantum physics stops feeling merely strange and starts feeling deeply unsettling, even to professional physicists. Entanglement is not a rare or exotic effect. It is not a theoretical curiosity. It is a core feature of how quantum systems behave, and it has been confirmed experimentally so many times that there is no serious doubt left about its reality. Yet, it remains one of the hardest ideas to explain without sounding mystical. To begin, imagine two coins. You place them in separate envelopes and shuffle them so you don't know which is which. If you open one envelope and see heads, you immediately know the other must be tails. This feels like correlation, but it's not entanglement. The outcomes were already fixed before you looked. Quantum entanglement is different. When two particles become entangled, their properties are linked in a way that cannot be explained by hidden instructions set in advance. The outcomes are not decided until measurement, yet they are perfectly coordinated when measured. This coordination does not weaken with distance. You can separate entangled particles by inches, miles, or light years. When one is measured, the other responds instantly in a correlated way, even though no signal travels between them. This is what troubled Einstein. He believed that nothing could influence anything else faster than light. Entanglement seemed to violate this principle, leading him to call it spooky action at a distance. But here is the crucial clarification. Entanglement does not transmit information faster than light. It transmits correlation, not control. You cannot use entanglement to send a message. You cannot choose the outcome of one particle to force a specific outcome in the other. The results are random but correlated. A helpful analogy is gloves. Imagine a pair of gloves created together and then separated. One goes to Earth, the other to Mars. If you open the box on Earth and see a left glove, you instantly know the one on Mars is right-handed. No signal was sent. The information was implicit. But entanglement goes further than this analogy allows. In the glove case, the handedness existed all along. In quantum entanglement, the specific outcomes do not exist until measured. Experiments show that if the particles had predetermined properties, their correlations would obey certain mathematical limits. These limits are known as Bell's inequalities. Quantum systems violate those limits. This is not speculation. It has been demonstrated in laboratory experiments with photons, electrons, and even larger systems. One famous set of experiments involved sending pairs of entangled photons to detectors placed far apart, with measurement settings changed randomly at the last moment. The correlations remained stronger than any classical explanation allowed. This rules out hidden instructions traveling with the particles. It also rules out local explanations, where each particle carries its own independent state. The universe, at least at the quantum level, does not respect strict separability. What does that mean, practically? It means that the state of a system cannot always be reduced to the states of its parts. Sometimes the whole contains information that the parts alone do not. This idea appears abstract, but it has real consequences. Quantum computing relies on entanglement to perform certain calculations faster than classical computers ever could. Quantum cryptography uses entanglement to detect eavesdropping with absolute certainty. Even experimental tests of space-time structure now rely on entangled systems. Entanglement also forces us to rethink what we mean by distance. In classical thinking, distance measures separation. In quantum thinking, distance measures difficulty of interaction, not independence of state. Two entangled particles can be far apart in space but still behave as a single system in terms of information. This does not mean space is an illusion. It means space is not the deepest organizing principle. Many physicists now suspect that entanglement is more fundamental than space-time itself. In some modern theories, space-time geometry emerges from patterns of entanglement. Regions of space that are strongly entangled behave as if they are close together. Regions with weak entanglement behave as if they are far apart. In this view, space is not a container where things sit. It is a structure that arises from relationships. This idea sounds radical, but it is grounded in serious mathematics, particularly in research connecting quantum information theory with gravity. One example comes from studies of black holes. The entropy of a black hole, which measures how much information it contains, scales with the area of its event horizon, not its volume. This hints that information is organized holographically. Entanglement appears to be the glue that holds space-time together. Even outside extreme environments, entanglement is everywhere. Electrons and atoms are entangled. Molecules exhibit entangled vibrational modes. In some materials, entire lattices of atoms exist in collective entangled states, producing exotic phases like superconductivity. Most of the time, entanglement is fragile. Interactions with the environment destroy it quickly, a process called decoherence. This is why macroscopic objects don't behave like quantum systems. But decoherence does not eliminate entanglement everywhere. It redistributes it into the environment. The universe is saturated with entanglement. We just don't notice it because it is spread across too many degrees of freedom to track. This leads to an important shift in perspective. Instead of thinking of particles as independent objects that occasionally interact, quantum physics invites us to think of reality as a web of relationships that temporarily stabilize into objects. Objects are not primary. Relations are. This does not erase individuality. It contextualizes it. An electron is still an electron. But its properties are not standalone attributes. They are defined through interaction. Entanglement does not mean everything is connected in a vague, spiritual sense. It means very specific mathematical correlations exist between systems that have interacted in particular ways. It is precise, measurable, and limited by physical laws. Still, it challenges deep intuitions. If parts of the universe are fundamentally relational, then absolute isolation is an approximation, not a truth. This does not mean the universe is conscious or purposeful. It means that separation is not as clean as classical intuition suggests. In the next part, we will explore how these ideas connect to measurement, decoherence, and why the everyday world appears classical despite being built on quantum rules. This is where quantum physics quietly explains why reality feels stable, even though it is not deterministic underneath. By this point, a reasonable question starts to form in the back of the mind. If the universe at its foundation is uncertain, relational, and entangled, then why does the everyday world feel so solid, so predictable, and so stubbornly classical? Why don't tables blur into probability clouds? Why don't coffee cups exist in multiple places at once? Why doesn't your phone randomly tunnel through the floor? This is not a small question. For decades, it was one of the deepest puzzles in physics. The answer lies in a process called decoherence, which sounds technical but describes something surprisingly familiar. Decoherence is what happens when a quantum system becomes entangled with its environment in such a complex way that its quantum behavior becomes effectively invisible. To understand this, imagine trying to listen to a single violin in a quiet room. You can hear every note clearly. Now imagine that violin playing in the middle of a roaring stadium. The violin is still playing, but its sound is drowned out by overwhelming noise. Quantum effects are like that violin. At very small scales, in carefully controlled conditions, quantum systems behave in ways that are delicate and precise. But as soon as they interact with a large environment, air molecules, light, vibrations, thermal motion, their quantum coherence spreads out into countless degrees of freedom. This does not destroy quantum behavior. It disperses it, Decoherence is not a collapse of the wave function in the philosophical sense. It is the rapid loss of observable quantum interference due to entanglement with the environment. This happens incredibly fast. For a microscopic particle in a vacuum, coherence can last seconds or longer. For a dust grain floating in air, coherence is lost in a tiny fraction of a second, far faster than any human perception. By the time you could notice anything strange, the quantum behavior has already been washed into the environment. This explains why macroscopic objects behave classically, not because quantum rules stop applying, but because they apply to everything at once. When a system becomes entangled with millions of surrounding particles, tracking its full quantum state becomes practically impossible. The system behaves as if it has chosen a definite outcome, even though fundamentally it has not. This creates the appearance of classical reality. Think of it like footprints in wet sand. At the moment a foot lifts, the sand briefly contains many possible shapes. But within moments, waves, wind, and gravity settle it into a stable pattern. The uncertainty didn't vanish magically. It just became irrelevant. In physics, decoherence selects stable patterns of behavior called pointer states. These are states that remain robust despite environmental interaction. Positions are one example. That's why objects tend to have definite locations rather than smeared out quantum superpositions. The world we experience is made of states that survive environmental noise. This insight resolved a major misunderstanding. For a long time, physicists believed that quantum mechanics needed a special rule explaining why measurement caused collapse. Decoherence showed that measurement is just an extreme form of environmental interaction. A measuring device is not special because it is conscious or macroscopic. It is special because it rapidly entangles with the system and the environment, dispersing quantum coherence beyond retrieval. This also clarifies why observation feels irreversible. Once quantum information spreads into the environment, reconstructing it would require controlling every interacting particle. In practice, this is impossible. That's why the arrow of time appears. The laws of quantum physics are time-symmetric, but decoherence introduces effective irreversibility through information dispersal. Milk mixing into coffee does not violate physical laws. It violates practicality. This brings us to a deeper idea. Classical reality is an emergent phenomenon. It is not fundamental. It arises from quantum laws interacting with large numbers of degrees of freedom. Just as temperature emerges from the motion of molecules, solidity emerges from quantum statistics. A chair feels solid not because it is rigid at the smallest scale, but because electromagnetic forces and quantum exclusion principles prevent atoms from occupying the same states. You are not touching the chair in the classical sense. You are being repelled by quantum fields. Everyday stability is built on invisible rules. This understanding has been tested experimentally. Physicists have observed decoherence directly in controlled systems, such as superconducting circuits, trapped ions, and cold atoms. They can measure how coherence decays as systems interact with their surroundings. They can even slow decoherence by isolating systems better, which is exactly what quantum computers attempt to do. Quantum computers work by preserving coherence long enough to perform calculations that classical systems cannot. This is extraordinarily difficult. The environment is relentless. Heat, noise, radiation, and vibration all work against coherence. The fact that we don't experience quantum weirdness daily is not because the universe is simple. It is because it is overwhelmingly complex. Now, this raises an important philosophical point. Decoherence explains why we don't see superpositions, but it does not explain why one outcome is experienced rather than another. This is known as the measurement problem. Different interpretations of quantum mechanics attempt to address this in different ways. Some propose that all outcomes occur, each in a separate branch of reality. Others propose hidden variables, or spontaneous collapse mechanisms. Some argue that the question itself is misguided. Physics, as an experimental science, remains neutral. All interpretations produce the same observable predictions. What matters is this: quantum mechanics works. It predicts experimental outcomes with astonishing accuracy. It underlies electronics, lasers, MRI machines, GPS corrections, and modern chemistry. You do not need to choose an interpretation to use quantum physics. You only need to accept that the universe behaves differently at fundamental scales than our intuition expects. This leads to a subtle emotional shift. The world is not fragile because it is quantum. It is stable because quantum rules allow stability to emerge. Uncertainty does not produce chaos. It produces structure. In the next part, we will move further outward, exploring how quantum principles influence time, causality, and the deep structure of reality, including whether time itself is fundamental or emergent. This is where quantum physics meets relativity, and where our understanding of reality becomes both more unified and more mysterious. Once we accept that the solid, everyday world is an emergent result of quantum rules playing out at enormous scales, a deeper and more unsettling question naturally follows. If matter behaves differently at its foundations, what about time? Time feels like the most stable feature of reality. It flows forward. It never pauses. It never reverses. Everyone agrees on it, at least in daily life. We plan our days around it. We age by it. We measure everything with it. But when physicists began examining time through the lens of quantum mechanics and relativity, that sense of certainty began to crack. In everyday experience, time feels like a river moving steadily in one direction. But in fundamental physics, time behaves less like a river and more like a coordinate, a dimension similar to space, yet not quite the same. In Einstein's theory of relativity, time is woven together with space into a single structure called space-time. Events do not simply happen in time. They happen at locations in space-time. Two observers moving differently can disagree on the order of events, how long something lasts, and even whether two events happened simultaneously. This alone already challenges intuition. But quantum mechanics goes further. At the quantum level, the equations that govern particles do not clearly distinguish between past and future. Most of the fundamental laws of physics work just as well backward as forward. If you reversed time in the equations, nothing breaks. And yet, we experience time as moving in only one direction. Why? The answer is not hidden in quantum mechanics alone, but in a concept we've already touched: entropy. Entropy is often described as disorder, but more precisely, It is a measure of how many microscopic configurations correspond to a macroscopic state. Systems naturally evolve from less probable arrangements to more probable ones. A dropped glass shatters. It never reassembles itself. Not because it is forbidden, but because the reassembled configuration is astronomically unlikely. The arrow of time we experience is closely tied to entropy increasing. This applies to quantum systems too. When quantum systems decohere, when information spreads into the environment, entropy increases. Information becomes harder to track, correlations become diluted, and the system appears irreversible. Time feels like it moves forward because information is constantly dispersing. Think of it like a message written in ink dropped into water. At first, the message is readable. Then it blurs. Eventually, it disappears into uniform color. Nothing fundamental was destroyed, but practical reversibility vanished. Quantum mechanics does not forbid time reversal. The universe simply doesn't cooperate with our desire to reverse it. Now, here is where things become even stranger. In some approaches to quantum gravity, time may not be fundamental at all. Several modern theories suggest that time might emerge from deeper relationships between quantum states, rather than existing as a basic ingredient of reality. In these models, the universe is not evolving in time. Instead, it exists as a network of correlations. What we perceive as time is the sequence of changes in these relationships. This idea sounds abstract, but we encounter similar effects in everyday life. A movie is not stored as motion. It is stored as a sequence of static frames. Motion emerges when the frames are played in order. In some quantum theories, reality itself may be more like a collection of frames, with time emerging from how those frames are related. Experiments cannot yet confirm this directly, but research in quantum cosmology and quantum information theory continues to explore it seriously. Another strange consequence of quantum time is that cause and effect may not always be well defined. In classical physics, causes always come before effects. But in quantum experiments involving entangled particles, correlations appear that cannot be explained by signals traveling forward in time alone. Some experiments suggest that events may not have a fixed causal order until they are measured. This does not allow time travel or paradoxes. It does suggest that at very small scales, the universe does not always commit to a clear before and after. Again, this feels disturbing only because we are used to thinking of time as universal and absolute. In reality, time behaves more like a local agreement than a cosmic law. Despite all this, your experience of time remains reliable. Your heart beats, your memories form, your body ages. Quantum uncertainty does not interfere with daily life. Why? Because just as classical objects emerge from quantum chaos, classical time emerges from quantum processes when systems are large and complex enough. Brains, clocks, planets, and stars operate in regimes where entropy and decoherence enforce a clear arrow of time. This does not make time fundamental. It makes it robust. One of the most comforting realizations here is that physics does not erase meaning. Even if time is emergent, moments still matter. Causes still lead to effects. Memory still distinguishes past from future. The universe does not dissolve into abstraction just because its foundations are strange. Instead, it becomes layered. At one layer, reality is probabilistic. relational, and deeply interconnected. At another layer, it is stable, predictable, and meaningful. Quantum physics does not take away our world. It explains why our world works at all. In the next part, we will explore how these quantum ideas scale up to the largest possible systems: black holes, space-time itself, and the limits of knowledge, where quantum mechanics and gravity collide. This is where some of the deepest open questions in modern physics live. When quantum mechanics meets gravity, the universe stops being polite. For decades, physicists have been able to describe the very small with quantum theory and the very large with general relativity. Both frameworks work extraordinarily well in their own domains. But when objects become both extremely massive and extremely small, like black holes, the two theories collide. And black holes turn out to be the most demanding exam the universe can give our understanding of reality. At first glance, black holes seem simple. They form when massive stars collapse under their own gravity, compressing matter into a region so dense that not even light can escape. Outside the event horizon, everything behaves according to known physics. Inside, classical theory predicts a singularity, a point of infinite density where equations break down. But quantum physics refuses to accept infinities as final answers. The real trouble begins with information. In quantum mechanics, information is sacred. The state of a system contains information about probabilities, correlations, and past interactions. And one of the most important principles of quantum theory is that information cannot be destroyed. It can be scrambled, hidden, or transformed, but not erased. Black holes appear to do exactly that. If something falls into a black hole, classical physics says its information is lost forever. The black hole eventually evaporates through a process called Hawking radiation, emitting thermal radiation that seems completely random. When the black hole disappears, the information appears gone. This creates what is known as the black hole information paradox. If information is destroyed, quantum mechanics breaks. If information is preserved, something about black holes must be very different from what we think. Stephen Hawking himself initially argued that information really was lost. Later in life, he changed his position, acknowledging that the paradox likely pointed to new physics. Modern research strongly suggests that information is preserved, but in an unfamiliar way. One idea is that information is stored on the surface of the event horizon itself, encoded in subtle quantum correlations. This leads to a remarkable concept known as the holographic principle. The holographic principle suggests that all the information contained inside a volume of space can be represented on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. This is not metaphorical. It emerges naturally from black hole thermodynamics. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This is deeply counterintuitive. It suggests that the universe may fundamentally operate with fewer dimensions than it appears to have. In some theoretical frameworks, our entire universe could be described as information encoded on a distant boundary. That does not mean we are illusions. It means that the structure of reality may be more about relationships and information than about objects floating in space. Black holes also force us to confront the limits of observation. The event horizon is not a physical wall. It is a boundary of predictability. Once something crosses it, signals can no longer reach the outside universe. For an outside observer, the falling object appears to freeze at the horizon, never quite crossing it. For the falling object, nothing special happens at that moment. Both perspectives are valid. Neither can access the full story. This duality suggests that reality itself may depend on viewpoint. In quantum mechanics, this is not new. Measurement outcomes depend on how and what we observe. Black holes simply amplify this lesson to cosmic proportions. Recent ideas propose that space-time itself may emerge from quantum entanglement. In this view, space is not a background stage where physics happens. Space is a network of quantum relationships. Where entanglement is strong, space is connected. Where it weakens, space stretches or even tears. Black holes may represent extreme rearrangements of entanglement. In some models, the interior of a black hole is not a place, but a reorganization of quantum information. The singularity is not a point of infinite density, but a signal that classical geometry has stopped being a useful description. This reframes the question of what happens inside a black hole. Instead of asking what happens to matter, we ask what happens to information. And that leads to a profound possibility. Black holes may not destroy information, but redistribute it so thoroughly that reconstructing it becomes practically impossible. Like shredding a book and scattering the pieces across the ocean, nothing fundamental is lost, but meaning becomes inaccessible. This idea preserves quantum mechanics while explaining why black holes appear irreversible. It also connects black holes to thermodynamics, entropy, and time. Black holes have temperature. They radiate. They age. They obey laws that mirror the laws of heat and energy. This suggests that gravity itself may be a thermodynamic phenomenon, emerging from statistical behavior of microscopic degrees of freedom. In this view, space-time is not fundamental. It is emergent, like pressure or temperature. No single molecule has temperature. Temperature emerges from many molecules together. Likewise, no single quantum interaction has geometry. Geometry emerges from many interactions together. This perspective has gained serious traction in modern theoretical physics. Black holes are no longer just exotic objects. They are laboratories where the deepest layers of reality reveal themselves. They teach us that space, time, and matter may all be secondary concepts, arising from something more abstract and more universal. Something like information. In the final part, we will step back from black holes and ask what all of this means for reality as a whole. What limits exist on knowledge? What questions may be forever unanswered? And what quantum physics suggests about the ultimate structure of the universe. By the time we reach this point, it becomes clear that quantum physics is not just a strange set of rules for tiny particles. It is a framework that quietly reshapes how we think about reality itself. What began as an attempt to understand atoms has grown into a theory that touches space, time, information, and the limits of knowledge. Along the way, it has forced us to abandon comfortable assumptions about how the universe should behave. Particles are not little balls. Events do not always have single causes. Nature does not reveal itself unless we interact with it. And perhaps most unsettling of all, the universe does not seem obligated to make intuitive sense. One of the most important lessons quantum physics teaches us is humility. The classical idea that the universe is fully knowable, predictable, and deterministic has not survived contact with experiment. Even with perfect equations, we are limited to probabilities. Not because we lack skill or technology, but because uncertainty appears to be built into the structure of reality. This does not mean the universe is random in a chaotic sense. Quantum mechanics is deeply ordered, mathematically precise, and astonishingly accurate. But it is ordered in a way that resists the idea of a single, objective story happening independently of observation. Instead, the universe seems participatory. Measurements matter. Context matters. Relationships matter. This becomes especially clear when quantum physics intersects with cosmology. The early universe was not just hot and dense. It was quantum. Tiny fluctuations governed by quantum rules were stretched by cosmic expansion and became the seeds of galaxies. Every large-scale structure we see today carries the imprint of quantum behavior from the universe's earliest moments. In this sense, the very shape of the cosmos is a frozen record of quantum uncertainty. Quantum physics also challenges how we think about time. At the fundamental level, many quantum equations do not distinguish past from future. The arrow of time, which feels so obvious in everyday life, emerges from statistical behavior and entropy, not from the deepest laws themselves. Time flows because systems tend to move from ordered states to disordered ones, not because time is pushing them forward. This raises uncomfortable questions. If time is emergent, what does that say about causality? About beginnings? About endings? Some modern theories suggest that spacetime itself emerges from quantum information. In these views, the universe is less like a stage and more like a web, where connections define structure. Space exists where information is entangled. Distance reflects how strongly systems are correlated. In such a picture, asking where something is may be less fundamental than asking, what is it connected to? Quantum physics also reshapes the question of reality versus description. We often assume that our theories describe an underlying world that exists independently of us. But quantum mechanics blurs that boundary. The theory does not simply describe outcomes. It constrains what can be said meaningfully about outcomes before measurement. This has led to decades of debate about interpretation. Is the wave function real or just a tool for calculating probabilities? Does the universe branch into many worlds, or does something else select outcomes? Are quantum states physical objects or summaries of information? There is still no consensus, and that may be the point. Quantum physics works exceptionally well without agreeing on what it means. Its predictions are verified to extraordinary precision. Technologies built on quantum principles now underpin modern society, from semiconductors to lasers to atomic clocks, meaning it seems as optional for effectiveness. Yet humans continue to seek it. What quantum physics ultimately tells us is not just about particles or equations, but about the nature of explanation itself. Some aspects of reality may be accessible only through mathematics, not intuition. Some truths may be relational rather than absolute. Some questions may be well defined mathematically, but impossible to answer in ordinary language. This does not diminish science. It deepens it. Science becomes less about uncovering a mechanical clockwork universe and more about mapping patterns, constraints, and possibilities. It becomes a way of understanding what can happen, not always why it must happen. Quantum physics also reminds us that our everyday experience is not a reliable guide to fundamental reality. Evolution shaped our intuitions for survival, not for understanding atoms or black holes. The fact that quantum behavior feels strange is not evidence that it is wrong, but that it operates far outside the conditions under which intuition evolved. When viewed this way, quantum physics is not mysterious. It is simply unfamiliar. And familiarity grows with exposure. As research continues, quantum ideas are increasingly influencing fields beyond physics. Information theory, computation, biology, and even philosophy draw on quantum concepts. The idea that information may be as fundamental as matter is reshaping how we think about everything from entropy to consciousness. Still, enormous questions remain unanswered. How exactly does quantum mechanics reconcile with gravity? What happens at singularities? Is space-time continuous or discrete? Does the universe fundamentally compute? Are there limits to knowledge imposed by physics itself? Quantum theory does not answer all of these questions yet, but it gives us the tools to ask them precisely. And perhaps that is its greatest gift. Quantum physics teaches us that reality is deeper than appearances, richer than intuition, and more subtle than classical logic allows. It invites us to accept uncertainty not as a failure, but as a feature, to recognize that knowledge has structure, limits, and layers. In the end, quantum physics does not tell us that reality is unknowable. It tells us that understanding requires new ways of thinking, ways that embrace probability instead of certainty, relationships instead of objects, information instead of substance. And in doing so, it quietly expands our picture of the universe, not by simplifying it, but by revealing how astonishingly intricate it truly is.